Hello everyone. Today we will solve the problem from the Zener diodes. Zener diode is a special type of diode and you can see the symbol is like this. Okay. So Zener diode looks like this one. Okay. Whereas normal diode it looks like this. Okay. This side is P, this side is N. Or you can say this is plus, this is minus. Okay. I think you already know that what is forward bias, what is reverse bias, right? I just show for the normal diode what is forward bias. If a diode connected with a voltage source like this way, where the P type connected with the positive and the N side is the connected with the negative, then we call this one is a forward bias. Okay, and if the diode is connected like this way, where the negative terminal of the voltage source connected with the P and the inside of the diode connected with the positive, then we can say this is the reverse bias. Okay, and we all know that the characteristics, VI characteristics will look like this one, right? Where this is the V, this is I, okay, and in the first coordinate, the barrier potential is 0.7 volt. After this one, the current will rise, okay? And in the third coordinate, in the reverse bias, after some times, it will go to the, after some time, it will go to the breakdown, okay? That means it will burn, or we can say this is the breakdown voltage. This is for the normal diode, okay? Zener diode is a special type of diode where the forward bias is exactly same with the normal diode. Okay, but in the reverse bias, after the breakdown voltage, it will not burn. What will happen? After the breakdown voltage, there will be a Zener breakdown. Okay, after that, this Zener diode will conduct. And you can see here the potential will be constant. That means suppose this generator voltage is 6 volt. Okay, that means if the input voltage of this Zener diode is below 6 volt, then this will in the cutoff region. Okay, but if the input voltage of this Zener diode is greater than 6 volt, then what will happen? A current will flow through this Zener diode and we will get 6 volt across this Zener diode. Okay, that means suppose there is a voltage source and I directly connected a Zener diode. Though we cannot do that one due to the current limitation, but suppose, okay, this is a variable voltage source and this is a 6 volt Zener diode, okay. Then what we will do, we will increase the voltage. If we increase the voltage up to 6 volt, that means if the voltage range is 0 to 6 volt, then at that time there will be no current will flow from point A to point B or through the near diode. Current will be how much? Current will be 0. That means we will see the current like this. Okay, and this point is 6 volt. After 6 volt, what will happen? Current will flow. Okay, this one for the reverse bias in the Zener diode. Okay, and after that one, if I connect a voltmeter here, then what you will see, this is for the current versus voltage, and if I plot V0 versus Vi, then what we will see? See, we will see that when we increase the voltage, at that time the input voltage increased, the output voltage also increased. Why? At that time the Zener diode will open circuit, will act as a open circuit, as the input voltage of the source is less than the Zener voltage 6 volt. That's why it will act as a open circuit. So up to 6 volt, the input voltage and output voltage is exactly the same. Just like we are measuring the input voltage source by the voltmeter, right? Now, when the voltage of the input voltage source is more than 6 volt, at that time what we will see? We will see that the output voltage, that means V0, across this Zener diode will be constant 6 volt. Okay, so that means if the input voltage of the source is greater than 6 volt, then we will get the constant voltage. Okay, that's why you call it a voltage regulator. I already have some video where I explain how a Zener diode works as a voltage regulator. Okay, but now here we need to solve the problem. So I will not go through in the details. Let's directly solve the problem. So I think you already have the basic concept. Okay. Now you can see here they ask us in the circuit below what are the current that flows through the 1 kilo ohm, 10 kilo ohm and the Zener diode. That means we need to know, suppose this is the I1, this is IZ and this is IL. Okay, we need to know I1, IZ and IL value. Okay, assume that the Zener has a breakdown voltage of 6 volt. That means this Zener diode will go to the breakdown after the 6 volt. Okay, this Zener diode voltage is 6 volt. Now, here you can see that the input voltage is how much is 10 volt. Okay, that means the input voltage is higher than the Zener voltage. So we can assume that Zener is in the on state. Okay, if the Zener diode is in on state, then this Zener diode will act as a voltage source or the constant voltage source. Okay, so here as this Zener diode voltage is 6 volt, we will get in this point will be 6 volt, this point will be 0 volt. Okay, now you can easily say what will be the value of I1? I1 will be 10 minus 6 divided by 1k, that means 4 milliampere. Easy, right? And as this point potential is 6 volt, or we can say this the voltage across this 10 kilo ohm is also how much is 6 volt. That means how much will current will flow? Then we can write down IL will be 6 divided by 10k. That means 0.6 milliampere. Okay, so if we apply KCL in this point, then what we can write down? We can write down I1 equal to IZ plus IL. Okay, from here we can write down IZ will be how much? IZ will be 3.4 milliampere. Okay, very easy. It's much easier than normal circuit theory problem or the transistor problem. Okay, now go to the next step. What will be the value of current if the 10 kilo ohm resistor is replaced by the 500 ohm? Okay, so go to the next page. Here they told us replace this resistance by 500 ohm, right? So let's redraw the circuit. 1k, Zener diode of 6 volt. This is 500 ohm. Okay. Now the approach will be exactly the same. As the input voltage is 10 volt, we assume the Zener is on. Okay. So if the Zener is on, this point potential will be 6 volt. This point potential will be 0 volt. Okay. So here I1 will be how much? I1 will be the same 10 minus 6 divided by 1k. That means 4 milliampere. Okay. Now what will be the value of IL? IL will be 6 volt divided by 500 ohm. That will be how much? That will be equal to 12 milliampere. Okay. Now just apply KCL in this node. We can write down I1 equal to IL plus IZ. Okay. So IZ will be how much? IZ will be I1 minus of IL. That means equal to minus 8 milliampere. Okay. So you can see here, as we change the resistance from 10 kilo ohm to 500 ohm, we saw that current flow through the Zener diode is how much? Is minus 8 milliampere. That means that is not possible, right? The Zener will on when some current will flow through Zener diode, right? But we saw that minus 8 milliampere is flow through the Zener diode. That means our assumption of Zener diode is on is the wrong. Okay, that means here the Zener diode is actually turned off. Okay, why generator is turned off? Now I will explain you that one. We saw that this is 1k, this is 500 ohm, this is 10 volt. Okay, and here we have the Zener diode. In last page, I show you that if we assume that Zener diode is on, at that time we saw that the current flow through the generator is negative. That means actually our assumption is wrong. The Zener diode is off. So let's turn off the Zener diode. That means I just open the Zener diode. Okay. Now you can see this is a normal circuit theory problem. That means a voltage source with series resistance of 1k and 500 ohm. So we need to know the voltage across this 500 ohm, or we need to know the voltage across this point A and this point B, right? That means VAB will be equal to VZ or Zener voltage, okay? And we need to calculate that one. How to calculate that one? VZ equal to or VAB equal to, just apply voltage division rule. 500 divided by 1000 plus 500 multiplied by 10, okay? That means equal to 3.33 volt, right? That means you can see here the voltage applied across the Zener diode is how much? Is 3.33 volt, right? But the voltage required to turn on the Zener diode is how much? Is around 6 volt, right? That means the voltage across the Zener diode is less than the voltage required to turn on the Zener diode, okay? What it will imply? It will imply that the Zener diode is actually turned off. As in the starting of the video, I already told you the Zener diode will turn on when the voltage across the Zener diode should be greater than the Zener voltage. Okay, you understand? That means the Zener diode is turned off for this case when the resistance is 500 ohm. And what is the voltage across the Zener now? Is around 3.33 volt. Okay, so that's all for this problem. Go to the next page. Here they told us the 12 volt 0.36 watt Zener diode. That means here they already provided VZ equal to 12 volt and the power P max equal to 0.36 watt. Okay. Zener diode operates at a minimum diode current of 2 milliampere. That means the Zener diode will turn on when IZ will be greater than 2 milliampere. So we can write down IZ minimum is equal to 2 milliampere. Okay. Determine the limits between which the supply voltage V can vary without loss of regulation. That means the Zener diode should be turned on. The Zener diode will act as a voltage regulator when the Zener diode is on. Okay. That means in other way, we need to know the input voltage variation such that the Zener diode will be turned on. Okay. Here they provided IZ min equal to how much? 2 milliampere. And we will get IZ max from this power condition. Is how much? P equal to how much? P equal to V into I, right? So that means I equal to P max divided by Vz. Okay. That means we can write down 0.36 divided by 12 is equal to 30 milliampere. We already have maximum current and minimum current. Maxima is the 30 milliampere, minimum is the 2 milliampere. Okay. Now we need to calculate the voltage V minima and V maxima. Okay. For this one, first we need to know when the Zener diode will turn on. That means the minimum voltage. This is the step one. Okay. They provided here this voltage is how much? 12 volt. If the Zener diode is on. Okay. That means this one is 12 volt. Okay. So this is the IL load current and we can write down load current is 12 volt divided by 1K, that is equal to 12 milliampere. Okay. And they told us the Zener diode will turn on for the minimum current of 2 milliampere. Okay. That means IZ min equal to 2 milliampere. If we apply KCL at point A, we can write down I1 or IS source current, that will be more specific, IS equal to IL plus IZ. Okay. That means is equal to 14 milliampere. Okay. So we need 14 milliampere from the source to turn on this Zener diode, right? So this potential is 12 volt. I assume that this potential is V minimum. Okay. So we can write down IS minimum. This will be the IS minimum. IS minimum equal to V minimum minus VZ divided by 100 ohm. Okay. That means V minimum minus 12 divided by 100 is equal to how much? 14 milliampere. So we can write down V minima equal to 12 plus 1.4 equal to 13.4 volt. Okay. So the answer is 13.4 volt when the Zener diode is just start. Okay. So we already got the value of minimum voltage. So now let's calculate the maximum voltage. Here we already know this potential is how much? This potential is 12 volt. And the maximum current Zener diode can tolerate is how much? 30 milliampere. I already calculated this one in the last page. Okay, and as this is 12 volt, then this load current will be how much? Is 12 milliampere, right? That means the maximum source current Zener diode can tolerate is equal to Is max is equal to 30 milliampere plus 12 milliampere. Okay, that means we can write down 42 milliampere. Okay, now exactly the same. In this point, the potential is V max. Okay, so Is max, just Ohm's law, equal to V max minus 12 volt divided by 100. Okay, I max is how much? 42 milliampere. V max minus 12 by 100. So V max will be how much? V max will be 12 plus 4.2. That means equal to 16.2 volt. Suppose this is output voltage V0, then we can plot like this. This is V0 and this is V input, okay? So what we can see? We can see that up to 13.6 volt, okay, then the Zener is turned off, okay? And then after 13.6 volt, this is 13.6, then Zener will be turned on, okay? Then up to 16.2 volt, Zener will be turned on, and then it will be, if we increase this one, then it will be burned. And this potential will be how much? 12 volt. Okay, very simple. So now in this problem, you already know how to calculate the minimum input voltage and maximum input voltage such that Zener diode will act as a voltage regulator. Okay, and there will be another problem that will be calculate the value of load resistance, calculate the value of source resistance, minimum and maximum. Okay, now go to the next problem. Very simple problem. What is the maximum permissible current through 5.6 400 milliwatt Zener diode? I already did in the last problem. Vz is how much? Vz is 5.6 volt. P is how much? 400 milliwatt. Okay. So what will be the Imax? Imax will be equal to 400 milliwatt divided by 5.6 volt. That one equal to how much? 71.42 milliampere. Okay. Now go to the next problem. Zener diode of 0.5 watt has a breakdown voltage 6 volt. That means they provided here Vz equal to 6 volt and P equal to 0.5 watt. Okay. From here we can calculate Iz max equal to 0.5 watt divided by 6 volt. That one equal to 83.3 milliampere. Okay. It is connected with a power supply of 0 to 10 volt. That means power supply range will be 0 to 10 volt. Okay. Assume that a maximum 60% power consumption is allowed in the Zener diode. Find the resistance that need to be connected in series with the Zener diode. Give the necessary circuit diagram. Okay. Here we already calculated Iz max, right, for the 100% consumption. Right, they provided here 60% consumption. That means we cannot calculate Iz max like this. Okay, so we need to consider 60% of the power. That means we can write down maximum permissible power P max we can use is a 60% of power specified. That means 60% of 0.5 watt equal to 0.3 watt. Okay, now we need to calculate I max will be 0.3 watt divided by 6 volt. That means equal to 50 milliampere. Okay, so here we can see 50 milliampere Zener diode can tolerate. Okay, now they told calculate the series resistance Rs such that Zener diode will not burn. Okay, then here this voltage source is 0 to 10 volt. This will be Rs, and here we have the Zener diode whose maximum current is 50 milliampere and Zener voltage is 6 volt. Okay, the Zener diode requires series resistance of Rs equal to how much? The maximum current can be flow is 50 milliampere, right? And the max voltage is how much? 10 volt. So we can write down 10 minus 6 divided by 50 milliampere. That means 4 divided by 50. That means equal to how much? It will be equal to 10 to the power 3 That means 4000 divided by 50 equal to 80 ohm. 80 ohm resistance needs to be connected in series with the Zener diode, okay, such that Zener diode will be safe. Okay, now go to the next problem. What are the current that flows through the 1 kilo ohm resistance and 10 kilo ohm resistance and the Zener diode? Find out the voltage. This problem is exactly same with the first problem, okay? So I will not go to that much details, just do the calculation, okay? Here you can see this voltage is how much? 6 volt, as this is 6 volt Zener diode, okay? So if this voltage is 6 volt, this current will be 0.6 milliampere, okay, load current. And here this current will be 4 milliampere. I already calculated, right? Is equal to 10 minus 6 divided by 1k, that means 4 milliampere, and IL will be 6 by 10k equal to 0.6 milliampere. So what will be the value of IZ? IZ will be 4 milliampere minus 0.6 milliampere, that means equal to 3.4 milliampere. Okay. Now to the next question. Here also the same. They told us to change the resistance to 1k. Okay. And we need to know the Zener diode is on or off. Okay. So we assume that Zener diode is turned on. Okay. If Zener diode is turned on, then this potential will be 6 volt. Okay. So go to the next page. Redraw the circuit. This is 6 volt. That means this current will be 6 milliampere. Okay. And this is 10 volt. That means this current will be 4 milliampere, right? Here also you can see IZ is how much? IZ is minus 2 milliampere, right? That means this generator is turned off. Okay. So what we need to do? We need to open the Zener diode. Okay. Now we need to recalculate the voltage. Now you can see this is a 10 volt voltage source and it connected with a 1k and 1k in series, right? So we can write down Vz will be 1 divided by 1 plus 1 into 10. Okay, that means equal to 5 volt, right? So here also you can see Vz is less than the voltage required to turn on the Zener diode. Okay, that's why Zener diode is turned off. So what happens if the 10 kilo replaced by 1 kilo? If we replace the 10 kilo resistance with 1 kilo resistance, then Zener diode will be turned off and this circuit will not act as a voltage regulator. Okay. Now let's go to the next question. For the given circuit, RS is 220 ohm, okay, and RL is 1.2k, and this Zener diode is 6.2 volt, and maximum current Zener can tolerate is 50 milliampere. Okay, so we need to know the value of Vi max and value of Vi min. Okay, so let's start with the Vi max, as they already provided here the maximum Zener current. Okay, so the maximum Zener current can flow is 50 milliampere. Okay, when the maximum Zener current will flow, this generator will be turned on. That means this is 6.2 volt. So we can calculate load current IL. How much? Then IL will be 6.2 volt divided by 1.2k. That means equal to 5.166 milliampere. Okay. So we already have the IZ max and IL, right? So the source current max will be 51.66 plus, will be 5.166 plus 50 equal to 55.166 milliampere. Okay, so now we can easily calculate the value of Vi max. Vi max minus Vz divided by 220 will be 55.166. Okay, if we solve this equation, we will get Vi max will be 55.166 multiplied by 2 and 220 into 10 to the power minus 3 milliampere as plus Vz is how much? Vz is 6.2 volt. Okay, so from here we can get this one equal to 17.23 volt. Okay, so we already got the value of Vi max. Now a little bit twist. In the last question they provided Iz minima. So in the same process with the same process like this, we can easily get the Vi mean, right? But here they didn't provide the Iz minima. So we need to solve this one in a different way. So I will show you two different ways. First is this will be turned on. This will be turned on when this is the 6.2 volt, right? This potential will be 6.2 volt. That means the voltage across this resistance is be 6.2 volt. Okay, this resistance is 1.2k. If we apply the voltage division rule, then we can write down V load equal to 1.2k divided by 0.2 plus 1.2 into Vi, right? I just calculate the output load voltage when Zener is off. I just need to calculate the optimum voltage, right? Such that Zener will be turned on. So we need to assume that Zener is turned off. At that time, what is the maximum voltage? I just do that one. When the Zener is turned on, at that time voltage will be how much? 6.2, right? So 6.2 will be equal to 1.2 divided by 1.4 into Vi. Okay, so Vi will be 6.2 multiplied by 1.4 divided 1.2. That one equal to 7.46 volt. Okay, this is the approach 1 or method 1. Okay, method 2. This is 220 ohm, this is 1.2k. Okay, here this potential is 6.2 volt. Here they didn't provide us the current, right? That means we can assume that Iz minima is 0 milliampere. Okay, that means this will be 0 milliampere. Okay, here the current will be IL. IL will be how much? IL will be 6.2 volt divided by 1.2k. That means equal to 5.166 milliampere. Right? So Is mean will be how much? Is minima will be 5.166 plus 0 equal to 5.166 milliampere. Okay. As we already have the Is mean, we can easily calculate the Vi minima. How? Is minima is equal to Vi in minima minus Vz divided by Rs. That means equal to Vi mean minus 6.2 volt divided by 200 ohm equal to 5.166 milliampere. Okay, so if we just multiply this one, then we will get Vi minima equal to 5.166 200 10 to the power minus 3 plus 6.2. That means equal to what we will get 7.23 volt. Okay, so the answer is same in both the way. Okay, if we do the method 2 or method 1, the answer will be the same as the 7.23 volt, but you can do any of the method. So that's all for the generator. Only these 6 problems came in the previous years. Okay, so in this one they didn't cover, CU didn't cover the source resistance variation problem and the load resistance variation problem. Okay, so I will show you source resistance variation problem and the load resistance variation problem maybe in the other video. Okay, that's all for this video. Thanks. Bye bye. Thanks for your time. Please do share this concept with your friends. And if you like this video, please press the like button. It really means a lot for me. Bye bye.